This clip is about the strategy design pattern. It's a great example of a pattern that encapsulates variation according to Larman's grasp principles. Before we start, let's look at a case study. Most e-commerce systems have to deal with different countries that have different address formats, tax rules, or freight costs. Perhaps we don't know yet to which countries we will ship or how this will be implemented exactly, but we do know that we can expect variation here. Now, in the general architecture, I assume that there is some sort of controller object that processes sales requests. Let's call this controller the sales order class. It handles stuff like filling out order details with a GUI, compute taxes, order processing, printing a receipt, and so on. It'll probably use other classes to help with this as well. So we know there is variation around handling different tax rates. How can we deal with this variation? We can copy-paste the code, we can use switches or if statements, or we can use inheritance with subclasses for each of the variations. All of these techniques have drawbacks. The first one we don't need to discuss. If you copy-paste code, that's bad. The second option is to use if statements to cover the variation. Here's a method to compute the tax. Depending on the country, tax is computed differently. Then we need to do something similar for shipping and for converting currencies. The question is, what happens if we want to start shipping to a new country? We need to change lots of pieces of code that are spread over different files. So this solution with the if statements inside each function leads to a lack of cohesion. Let's look at another solution, inheritance. So if you have the sales order class, we could introduce new subclasses with different functionality depending on the country. Tax calculation is now handled in a subclass that's specific to a country. So the NL order class would compute taxes according to the Dutch rules, and the UK order class computes them according to the rules in the UK. When you deal with the order in the system, depending on the country, you create either an NL order or a UK order. This looks like a better solution than the previous one, but there are some issues here as well. How about dealing with different languages in one country, like in Belgium or Switzerland? Different date formats, different shipping costs or address formats, and how can we share code between them? Most countries in Europe use the euro, and we don't want to copy-paste the currency conversion code for each country that has the euro. If we add a variation like a date format, we need to change the order subclass for every country to deal with this. A better approach is to find what varies and encapsulate that in a class of its own. Then contain this class in the original class. Favor aggregation over inheritance, remember? To follow this advice, we need to introduce a separate class, CalcTax, since tax calculation varies across different countries. Every sales order object should then have a CalcTax object. In the UML diagram, this is what it looks like. We have a sales order class that aggregates a CalcTax class, and CalcTax is an abstract class that encapsulates the variation in tax calculation. Then we have an NL tax and UK tax subclass that each have the tax implementation specific for that country. Here's another example where we can apply exactly the same principle. The movie rental example we've seen before. Different movies have different rates. Children's movies, standard movies, recently released movies we need to introduce a separate class to encapsulate this variation. There will be 3 subclasses, each of which represents the rate calculation of a particular type of movie. And finally, every rental object should then have a rate calculator object. Here's the UML diagram that illustrates this approach. Rental has a rate calculator class via an aggregation, and new movie, children's movie, and standard movie are subclasses of rate calculator that each have their specific rate calculation algorithm. In code, we have a rental class that refers to a rate calculator, and the rate calculator is an abstract class with an abstract method to calculate the rate. And for each rate, we have a specific subclass. Here's the example of the new movie rate calculator. The other 2 rate calculators will look very similar to this one, but the body of the calculate rate method will obviously be different. This solution is better than the previous inheritance solution because the cohesion is much stronger. There's one place where rate calculations happen, and it's also easier to change later on because movie doesn't need to decide on its rental price. And similarly, sales order doesn't need to decide how to compute the taxes. If a movie is no longer new, future rental will automatically assign the right rate calculator. Now, inheritance isn't in principle a bad thing. This solution also uses inheritance. New movie calculator is a subclass of rate calculator after all, and NL tax is a subclass of tax calculator. However, we use inheritance here very carefully and to capture one single kind of variation. Now, this approach to encapsulating variation is actually a design pattern that's called the strategy. The idea is that you define a family of algorithms, tax calculation algorithms, for example, and make it possible to select one of these strategies, Dutch tax or UK tax or whatever, without having to change anything anywhere else in the code. Here's an overview of the strategy pattern and the problem that it solves. Overall, the abstract class specifies the interface to each algorithm. For example, you need to know the price to compute the tax rate. Each concrete strategy implements a particular algorithm. NL tax computes Dutch tax, UK tax computes tax in the UK. As a consequence, you don't need that many switches or ifs, and you also standardize the way each algorithm is used. This is the generic UML diagram of the strategy pattern. As you can see, the movie and sales order examples that we looked at before follow exactly this structure. Concrete strategies may need some extra information when computing the tax rate. For example, the Dutch tax system has 2 levels of taxation, depending on the kind of product or service. This kind of information can be passed as a parameter when you compute the tax, or you could configure the NL tax object when you create it. The context in which these strategies are used is responsible for supplying this information. Another advantage of the strategy pattern is that you can very easily test each strategy, since the strategies themselves are mostly independent of the rest of the code. So you can write a test to check that NL tax compute Dutch tax correctly by giving it a few test values and checking that the result is as expected. You don't need the rest of the application to do that. Now let's extend the sales order example a bit and apply the strategy pattern there in more places. We dealt with the variation in tax computation, but let's now also use the strategy pattern for currency conversion and language. For each of these two variations, we use a separate strategy pattern. Each pattern introduces a new abstract class to encapsulate that variation. This means that in the end, we aggregate 3 objects in the sales order class. One for tax, one for currency, one for language. So, the context class, which is sales order in our example, will contain 3 different strategy objects: taxes, currencies, and language. Each of these different strategy types has an abstract class that defines the interface, and specific subclasses, the concrete strategies, that contain the actual implementations. In the sales order class, we create the concrete strategies relevant for this particular sales order. If the sales order is for the Netherlands, we want to use the Dutch tax rate, the euro currency, and the Dutch language. And we do the same for every other country. We indicate what tax, currency, and language settings we use. The nice thing here is that we can now share currencies and languages between countries. So even though Ireland and the UK are different countries, we can still reuse the English language strategy. When we actually deal with taxes, currencies, and languages, we refer to the tax, currency, and language strategies. But we don't need to know anything about the actual implementations that are used. If we introduce new countries, tax rate changes, or currency conversion changes, or language translations are updated, we don't need to change anything in the part of the code that uses the strategies, because these changes are all encapsulated behind each abstract strategy. The strategy is an example of a slightly more advanced pattern. It separates using calculations from defining them, and it relies on abstract classes to achieve this. Now, I know what you're going to say. Hey, you said we would get a joke with each design pattern. So here it is. What's a surrealist strategy to screw in a light bulb? A fish. Thanks for watching, and catch you in the next one.